We're going to continue with the example of a die, but instead of wanting to measure which face ends up face up, we're going to measure where the die lands in this direction. And I have a ruler here, and I'm going to allow the die to land between 0 and 24 centimeters. And I'm going to do it with a resolution of 2 centimeters. So there's a total of 12 possible locations in this direction that the die can land. So as we have 12 possible measurement values, that means we have a 12-dimensional vector space. So it could land in position 0, in which case it has a 1 in the first component, and then it has 11 zeros. Or it could land at the location 2 centimeters, and then it has a 0 in the first component, and as this is the second possible location, there's a 1 in the second component, and then the remainder are all zeros. And this goes all the way up to the final possible location, which is 22 centimeters, and it has zeros for the first 11 components, and then a 1 for the final component. So as always, we can define an equal probability vector. That's going to represent the dice before it's been thrown, and we don't know where exactly it's going to land. So it has equal probability of ending up in any of these states. So each component is 1, and we have to normalize that, so we put a 1 over root 12 in there. We're also going to define a second useful vector, which is the vector that represents the state where the die lands in the first quarter of this direction. So with the possibility of, that's the first half, 12 centimeters, and landing in the first quarter means landing in the first 6 centimeters. Now at this resolution there are 3 possible states which correspond to the first quarter. So we'll call this the Q vector, and it has to be in one of the states 0, 2 or 4, which means it can be up to 6 centimeters in this direction, and all the other components have to be 0. And again, we have to normalize this. We'll put a 1 over root 3. Hopefully by this time I don't have to prove that this is going to normalize to 1. Now we're going to focus on a specific problem, namely what is the probability that it lands in the first quarter, given that there's an equal probability that it could land anywhere. So before we throw the dice, it's in the equal probability state. So what's the probability that it will end up in this state, the first quarter state? Well, we can apply our normal rule, the probability that it lands in the first quarter, given that there's equal probability of landing anywhere. And we're going to keep our magnitude sign here, even though we're not using complex numbers at the moment. We know that we might have to, so we'll keep the magnitude in so that we can deal with complex numbers later on. And the rule is we take the inner product of Q with E and we square the magnitude. So let's actually do that. Q is 1 over root 3, and it's 3 1s and the remainder are zeros, times 1 over root 12, and they're all 1s, and square the magnitude. So we have 1 over root 3 times 12 is 36, and root 36. And we have 1, 2, 3 of these are actually going to give us a value, and the rest will be 0. So there's a 3 there, all squared. And that equals magnitude of 3 upon 6 squared, which is a half squared, which is a quarter, which is exactly what we would expect. So our rule works, the calculation comes out fine. I've drawn these two vectors now in graphical form. This is the first quarter vector. It's got 3 elements, each of which has height 1 over root 3. And as I've emphasised here, this is not to scale here. And the equal probability vector, it has got 12 entries, each of which is of height 1 over root 12. And it spans all the distances from 0 centimetres right up to 24 centimetres. And the resolution, the distance between the components, is what I've labelled delta x here. It's the total length of the ruler, 24 centimetres, divided by the number of intervals, which is 12, and so this value is 2 centimetres. What we're going to do is we're going to increase the value of n. So we're going to pack these lines tighter and tighter together. Delta x is going to become smaller and smaller. And we're going to continue to evaluate our probability. What's the probability of landing in the first quarter, given that it could be anything to begin with. And eventually, these lines are going to pack this area so tightly that it becomes completely filled, and we will move towards an integral instead of just the summation of the components. So let's increase n to an arbitrary number. So there will be n of these entries now, and the normalization constant will be 1 over root n. And whatever n is, there'll be 1/4 of the number of n elements in this vector here. And let's assume for the moment that n is a nice tidy integer multiple of 4. So this will become root n upon 4. And we'll fill the same in here, root n upon 4, root n. And the distance between the elements now becomes 24 over n. Now let's just evaluate our probability. Probability of landing in the first quarter, given that there's equal probability of any value. So we take magnitudes, and it will be 1 over root n upon 4, and there will be n upon 4 of these, and then the rest will be zeros, and multiply that by root n, and there will be n of these, the whole thing squared. Just do the calculation. We've got 1 over root n squared upon 4, and this will only produce the number n upon 4 all squared, which equals root 4 is 2, root n squared is n, and now we've got the n upon 4 equals, well, it's a half squared, which is a quarter, which is the correct value. I'm just going to repeat that calculation, but in a slightly more formal version. If we call each of these entries Q1, Q2, Q3, or Qi, and these E1, E2, up to En, then we can write that calculation down as the summation from I equals 1 to n, and we have the normalization constant for this, which is 1 over root n upon 4, and Qi, remembering that Qi is 1 up until the value equals I equals n upon 4, and then we have 1 over root n here, and we have Ei, and each of these has the value 1. then this will equal, well, there'll only be n upon 4 values, because after n upon 4 this is 0, so we get 1 over root n squared upon 4, n upon 4, and this is the same as we had before. Forgot to put the squares in there. We've got 2 upon n by n upon 4, which is a half squared, which is a quarter, as before.